Excellent, excellent. Okay. I suppose the next natural thing to talk about is something called the transition probability matrix.
Okay, let's do that.
Let's do that. And the reason why is because although these diagrams are nice, there's not much you can do with this. I can even put I could put numbers on all of these things. I could put a 0.2 here. These both 0.4, 0.4. I don't know. I guess this is going to be 1 and 1 because they don't go any other direction.
Okay.
But this, although it tells you everything about it and you know exactly what all these probabilities are, the chain is fully characterized by this diagram. You can't do too much analysis with this. If I asked you a really tricky question about this chain, you'd probably go at it with a bunch of different probabilities chained together, and it would just be very cumbersome.
Right. Okay.
And an easier way to store all of these values.
Sorry, Chris. Before you move forward, should these two probabilities add up to 1?
No, because
right. Okay, right.
Otherwise,
sorry.
Yes. Otherwise, yes.
Sorry. Thank you. Yeah,
no
right.
problem.
Right. So one can go to itself, or go to 2 or 3, but these 3 probabilities have to add up to 1. Okay. Right. Good. Sorry, I interrupted you. We're talking about the transition probability matrix.
What makes more sense is the idea of putting these in some organized structure.
Right.
What we would like
And Chris, if you could make sure when you finish writing the matrix, back off a little bit so that everybody can see the matrix on the board.
What we would like is we can write this matrix. We'll just call it. This is the way they always call it, just a big P, kind of vague notation. But what we'd like is some matrix that tells me what all of these probabilities are. And so the way we typically write this notation, and this is purely a choice that has been made, is we write it such that the ij element of this matrix is equal to the probability of going from state I to state j.
Okay.
So for example, in the 1, 1 spot, you have the probability that x1 equals 1, given x0 equals 1.
Okay.
The 1, 2 spot, you have the probability that x1 equals 2, given x0 equals 1.
Okay. So the conditioned state is along the rows.
Yes, this is the conditioned state, and this is the
present state.
Yeah, the present state. You can think of it like that.
Right. Okay.
And so what ends up happening is you end up with this very particular matrix, and this matrix has a couple of rules it's going to have to follow, obviously.
Yes.
The first is that the sum across all of the rows has to be 1.
Right.
Simply because these are all defined probability spaces, so they're just going to have to equal 1 at the end.
Yes.
And that's I guess the biggest constraint. There's a few others, and there's some very good properties about this, but I guess let's just write out this example we've seen here. Once you get used to looking at these things, it's way better than looking at this. You get a much better feel for the system.
Right. I'm just going to pull this a little bit this way just so that
there's
more room. Yeah. Okay. Go ahead.
So we'll write out this matrix or this system we've drawn here a little bit.
Right.
So we have the probability of going to 1 from 1 is going to be 0.2, to 2 from 1. It's going to be 0.4. That's this one right here. And then to 3 from 1, we don't even need to look at the diagram because we know it has to sum to 1, so we know it's 0.4.
Right.
Then from 2, we can't go back to 1, so there's a 0 there. From 2, we can't stay at 2, so there's a 0 there. But we can go to 3, so we have a 1.
Right.
Similarly, from 3, we can't go to 1, so we get a 0. We can go to 2, and we're going to always go to 2. And we can't stay at 3, so there's another 0.
Right. And of course, they all add up to 1 along the rows.
Yeah.
Okay.
And this matrix, I guess, humble as it is, defines pretty much all of the mechanics, all of the dynamics. Everything you need to know about a Markov chain is encapsulated by this one small matrix.
Right.
I mean, it's small here, but you can imagine if you had 10, 15, 20, as many states as you want, this thing gets quite large.
Yes.
And in the case of a countably infinite set, you have an infinitely dimensioned matrix.
Right.
Which is not super good to look at, but you can still mathematically address in a lot of different ways.
Right.